let us move on to see a more general case of a PDE which involves examples including Burger's equation for shock mechanics, or the telegraph equation, or the KdV equation for water waves, or the wave equation or the diffusion equation. So, I am going to look at the solution of the most general constant coefficient PDE using my joint Fourier Laplace transform. So, let us continue our discussion. So, what I have is the following. So, I am given, so let me call this PDE as follows: linear homogeneous, so linear homogeneous fractional evolution equation. Okay. So, let me call this as a linear homogeneous fractional evolution equation. So, the equation is as follows: this is the alpha-th derivative of u plus c times del u del x minus nu times del square u del x square plus b3 times, let me just include all different derivatives of u. So, third derivative and so on. So, let me include the nth derivative of u del n u by del x n, and let me call the right hand side as q of x comma t. Okay. So, let me try to solve, let me give all the initial conditions. The initial conditions are as follows: u of x comma 0 is f of x, and I am given the boundary condition u of x comma t is 0 when the domain size grows to infinity. Okay. This is for all t greater than 0, and let me further assume that my fractional order is from 0 to 1. Okay. So, note that if I were to take c non-zero and all the other coefficients nu, b3, b4, b and 0, I get my advection equation, or if I take c equal to 0 and nu non-zero and all the other coefficients 0, I get my diffusion equation, and if I take b3 non-zero, my KdV equation. So, all the equations are enveloped in this giant PDE. So, let me just try to solve this PDE and give the most general solution to this constant coefficient PDE. So, let me just start by right away applying, let me call this my expression 1 and these conditions as my 2. So, I am going to apply my joint Fourier Laplace transform. So, let us apply joint Fourier Laplace transform to 1, and I see that I am going to get, so after all the simplification I am going to get my following expression for the joint Fourier Laplace solution in the transformed plane as follows. So, this is the Fourier variable and s is with respect to time. So, that is my Laplace variable. So, the Fourier is with respect to x and my Laplace is with respect to time variable t. Okay. So, then the solution is as follows: I can write this as f tilde of k times s to the power alpha minus 1 divided by s to the power alpha plus a. Let me call this constant as a square, plus the transform of the right hand side q function. So, I get this is the joint Fourier Laplace transform of q of k comma s times 1 by s to the power alpha plus a square, where my constant a square includes all the factors involving the constant coefficient. So, a square is given by this following expression I k c plus nu k square nu coming from the diffusion term, and then plus I k q b 3 plus and so on. So, let me just include the nth term here I k to the power n b n. We see that a square envelopes all the different types of spatial derivatives that are included in this giant PDE. So, which means that I can always invert, let me call this as my expression 3, I can always invert my expression 3 to come back to my original solution to the PDE. So, if I were to apply inverse Fourier Laplace transform, to 3, I get the following expression. I get that my solution u is as follows: u of x comma t is 1 by square root 2 pi integral negative infinity to infinity of this following integral f tilde of k times the Mittag-Leffler expansion E of alpha comma k. So, alpha is alpha and beta is 1. So, E of alpha comma 1 of the argument negative a square and times t to the power alpha e to the power I k x d k. So, that is my inverse transform, the Fourier inverse transform, plus 1 by square root 2 pi coming from the second expression. I see that this is going to be the Fourier inverse of the convolution integral. So, the convolution integral is as follows: 0 to t tau to the power alpha minus 1 d tau, and then the Fourier integral is as follows: integral negative infinity to infinity q tilde of k comma t minus tau times the Mittag-Leffler expansion E of alpha comma alpha of the argument negative a square times tau to the power alpha times e to the power I k x d k. Okay. So, that is my second integral coming out of the inverse transform of the right hand side. Okay. So, this further evaluation of this solution is not possible at this stage, because we are not given the form of f and q. However, I just want to give you the following remark: this particular equation encompasses lots of different types of PDEs, namely the cases that are included in this example. So, cases included as are, if I am given that nu is non-zero, there is no diffusive term, then I am dealing with the wave equation. Okay. So, the general wave equation. Suppose if I have the coefficient of the third derivative B3 not 0, and even the coefficient of the first derivative not 0, the first derivative with respect to space, then I have the famous KdV equation, the fractional KdV equation for shallow water models. And then if I have that B3 is non-zero, C non-zero, and even the diffusion term non-zero, I have the KdV equation, the KdV Burger's equation, which models the shock in a fluid. Okay. So, this is for acoustics and gas dynamics. Okay. So, then let us look at another example. So, the second example is, well, this particular example will be for another fluid flow case, that is the unsteady Coit flow. Okay. So, let me just briefly highlight what is this Coit flow. So, the unsteady Coit flow. Okay. So, suppose we are given a pipe. So, and pipe in 2 dimensions. Okay. So, let me say that we can assume it is a pipe, or we can assume that there are 2 plates in between which there is a fluid flow. So, such flow where we have such bounded flow between 2 plates is said to be a Coit flow. Basically, this is a flow in a finite domain. Okay. So, we have a fluid flow in a finite domain here. So, let me write down the type of problem we are solving here. So, this is unsteady viscous fluid flow between two plates at z equal to 0. So, let me call that the plate at z equal to 0 is at rest, and the second plate z equal to h is in motion. The z equal to h plate is in motion, which is parallel to itself with variable velocity u of t, okay, in x direction. Okay. So, let me just set my frame of reference. My x direction is the following, this is the following x direction, and my z direction is perpendicular to this. So, this is my z direction, and I am further given. So, the equation that we are solving for the fluid flow in this case is the standard diffusion, the fractional diffusion equation, del alpha u del T alpha given by is equal to nu times the second derivative of u plus some extra forcing term, which typically denotes the pressure developed by this fluid flow. So, some extra forcing term, let us say this is P of t. Okay. So, now I am solving this solution in a finite domain z from 0 to h and for all non-negative time. So, I am given the boundary condition are as follows: u of 0 comma t is 0 and u of h comma t is u of t, and this is for t greater than 0. Okay. So, these are my boundary conditions. So, this is second order in space, and my initial condition is u at z comma t is 0 for all t non positive. So, let me just denote these are my boundary condition. I am not given the order of the fractional PDE here, and this is for all z from 0 to h. Okay. So, then what I am given is the following. So, let me call this as 1 and let me call these initial and boundary conditions as 2. Okay. So, solving 1 and 2, let us look at the solution to 1 and 2. So, now, well, why I brought up this particular example is the following. Since we are solving in a finite domain, I cannot apply, our domain is as follows 0 to h and t is greater than 0. We see that my domain in the z direction is finite, and my PDE, well, my PDE is with respect to the z derivative. So, I need to correct. So, the derivative is with respect to z. So, del alpha u del T alpha is equal to nu times del square u del z square plus P of t. Okay. So, although the domain in x is infinite, it is the domain in z that matters. Okay. So, this is, please correct this equation here. So, this is the correction for this particular coed flow example. Okay. So, what is important is that we are solving our solution, we are finding our solution for a finite domain problem. So, which means our regular application of Fourier transform or Laplace transform is not going to work, and we may have to resort to Fourier series, because for finite domain we can use the so called periodic boundary condition, and that is where my Fourier series is going to play a role in the solution to this PDE. So, for half plane or finite domains, for half planes or finite domains, this case we have to apply joint Laplace transform, but Fourier Laplace transform, but Fourier series. Okay. So, Laplace transform, but Fourier series. Okay. So, what I see is, now notice that I am also given my boundary condition as a Dirichlet condition. So, since boundary conditions are Dirichlet conditions, because we are given the solution on the boundary. So, we have Dirichlet condition, we are going to apply Fourier sine series, apply Fourier sine series. Okay. So, whenever we are given Dirichlet condition, we apply Fourier sine series, and the typical method is, if we are given Neumann condition, apply Fourier cosine series. Okay. So, then if we do that, my joint Fourier Laplace solution is as follows. So, instead of a k, where k was from negative infinity to infinity, I now have n. Okay. So, n or n comma s. So, this is my Fourier series variable, transformed variable, and s corresponds to time, is my Laplace transform variable. Okay. So, Laplace transform variable. Okay. So, then I have, this is the integral from 0 to infinity e to the power negative s t dt, integral 0 to h u of z comma t. So, I have now written it in the form of sine. So, notice that the application of the sine transform brings in this factor sine of n pi z by h dz. Okay. So, the Fourier sine series brings in this factor instead of this kernel, instead of the exponential kernel. Okay. So, then when I apply my sine series, I get that I can evaluate this interior integral. This interior integral after evaluation gives me the following expression. This is going to be, well, this is going to be this P s bar. This is the Fourier, well, Laplace transform of this quantity p of t times 1 by a times 1 minus of minus 1 to the power n divided by s to the power alpha by nu a square, where my factor a is these frequencies n pi by h. Okay. And my n is 1, 2 and so on infinity. Okay. So, these are my factors, and plus the second term is nu times a times minus 1 to the power n plus 1 of u bar of s the solution, divided by s to the power alpha plus nu a square. Okay. So, then if I I have already applied Fourier and Laplace transform. So, let us now invert the solution. So, if I were to invert, so let us invert by applying the inverse Laplace transform, and I get that my solution in the Fourier space u tilde s of n comma t. So, I am first applying the Laplace transform here. This is going to be this factor taken out 1 by a 1 minus negative 1 to the power n times integral. Notice that my Laplace inverse integral is going to be the convolution of these two factors p of s and 1 by this factor. So, I get this following convolution p of t minus tau times, again the Mittag-Leffler expansion, tau of alpha minus 1 e of alpha comma alpha of nu a square tau of alpha, okay, d tau. So, that is my first integral, and after applying the inverse transform in the second integral, I get the following convolution. The convolution is nu a minus 1 to the power n plus 1 times integral 0 to t times the convolution of u. So, u of t minus tau times again the Mittag-Leffler expansion tau of alpha minus 1 e of alpha comma alpha of the same argument nu a square tau to the power alpha, okay, and then d tau. Okay, so then, well, we have already now, let me just rewrite this expression to show you what's the stage of the solution here. So, after rewriting, this is my Fourier, my solution is still not arrived. This is solution in the transformed Fourier space, but the physical time. The solution is as follows again. So, this is 1 minus 1 to the power n times integral 0 to t p of t minus tau to the power alpha minus 1 e of alpha comma alpha of nu a square tau to the power alpha d tau plus nu a minus 1 to the power n plus 1 integral 0 to t u of t minus tau times tau to the power alpha minus 1 e of alpha comma alpha of nu a square tau to the power alpha, okay, and the integral with respect to tau. Now, then when I apply my inverse sine transform, when I apply inverse sine transform and this time on a finite domain, instead of the transform being the integral transform, this is going to be a Fourier sine series. So, my Fourier, so after applying the inverse sine transform as a Fourier series, I get my original solution as follows: u of z comma t is, well, 2 by h, the Fourier series is as follows: n from 1 to infinity u tilde of n comma t sin n pi z by h. So, where u n, let me call this as my expression number 3. So, where this particular transform is coming from expression 3. So, after substituting this solution from expression 3, I get back my solution in the physical plane by summing up this particular series. So, that completes the solution to this example, and also our discussion on fractional calculus and fractional PDEs. Now, in my next set of 2 lectures, I am going to come and discuss on a new transform which has revolutionized almost entire engineering and physics, starting from biomedical engineering to signal processing to physics to science, you name the area, and this particular transform is always there, and that particular transform is the wavelet transform. So, thank you for listening today, and we will meet next time. Thank you.